Okay, today we are finally, at long last, wrapping up chapter 7 with 7.7, which talks about variation and problem solving. So we are talking about solving problems involving direct and inverse variation. So these are another type of application problem in chapter 7. Woohoo, there's so many. I know you're all stoked about it. But yeah, let's get into these problems. So part 1. Solving problems involving direct variation. So we say that y is directly proportional to x if there's a non-zero constant k such that y is equal to k times x. And the number, so k represents some constant that's not zero, and that number, k, is called the constant of variation or the constant of proportionality. So we're going to do a couple example problems here. There's some kind of easier variation problems, and then there's some harder application type ones. So we're going to start with easy and then move to hard. So suppose that y varies directly as x. If y is 5 when x is 30, find the constant of variation, and then also the direct variation equation. I'm going to add that. And the direct variation. Okay, so first off, we need to find the constant of variation k. So we know that y is equal to k times x. We're talking about direct variation. And further, we know that y is 5 when x is 30. So that simple piece of information allows us to set up the following equation. 5 is equal to k times 30. And then in order to solve for k, we divide by 30. So 5 over 30 is the same thing as 1/6. So k is equal to 1/6. And then after we find the constant of variation, we just plug that back into the direct variation equation right here. So y is equal to kx. In this case is y equal to 1/6. I don't know why that happened. Y is equal to 1/6 x, or x over 6. And that is our equation for the direct variation equation of this problem. So k will change depending on the information that you're given in the problem. In this case, it's 1/6. But if it had been different numbers, then we would have gotten a different constant of proportionality, etc. Okay, so that's an easy problem. Now we're going to do a hard problem. So a hard problem. So Hooke's law. Hooke's law states that the distance a spring stretches is directly proportional to the weight attached to the spring. If a 40-pound weight attached to the spring stretches the spring 5 inches, find the distance that a 65-pound weight attached to the spring stretches the spring. So the first thing that we need to do is we need to know the constant of proportionality. And in order to find that, we're going to have to write an equation, right? So we are given that the distance a spring stretches is directly proportional to the weight attached. So I'm going to put D as distance stretched, and I'm going to put W as weight attached. And since I know D is directly proportional to W, I'm going to write D is equal to K times W, where K is, again, that constant of proportionality. And now I'm going to use the information given to me in the problem to solve for K. So that's the first part of these application problems. Solve for K, then solve for what they're asking you to solve for. So we know that a 40-pound weight stretches a spring 5 inches. So a 40-pound weight stretches the spring 5 inches. So D, 5 inches, equals K times weight, 40. So divide by 40. 5 over 40 is the same thing as 1/8. So we know that 1/8 is equal to K. So our equation now is D equals 1/8 W. And now we want to know, find the distance that a 65-pound weight. So we know that now W is 65. So D equals 1/8 times 65. So D is equal to 65 over 8, which is approximately, D is approximately 8.125, and the units of my distance stretched are inches. So it turns out that a 65-pound weight would stretch the spring a little bit over 8 inches. Okay, so these problems are hard when you first read them, but the 2 steps are solve for the portion, solve for K, the constant of proportionality, and then solve for what they're asking you to do. And you just need to reread the problem, take it piece by piece. Don't freak out, just take it nice and slow. You got it. So that's direct variation. And now this is inverse variation. Y is inversely proportional to X if there's a non-zero constant K such that Y is equal to K over X. So direct variation was Y equals KX. Indirect is Y equals K over X. Okay, and again, K is still the constant of variation in both examples. So let's talk about an easy example and then a hard example. So easy. Suppose that U there is inversely as W. So, or if U is 3 when W is 5, find the constant variation in the inverse variation formula. So since U varies inversely as W, we have U is equal K over W. U varies inversely when as W, so that's going to be U equals, U varies, U equals K over W, inverse variation. Then we know if U is 3 when W is 5, find the constant variation. So we're going to multiply that 5 up. 3 times 5 is 15, so 15 is equal to K. So our constant of variation for this problem is 15. Then the inverse variation problem is U equals K over W, except for now we know that K is 15, so it's going to be U equals 15 over W. And that is our inverse variation equation for this problem. All right, moving on to a hard problem. So Boyle's law says that if the temperature stays the same, the pressure P of a gas is inversely proportional to the volume V. If a cylinder in a steam engine has a pressure of 960 kilopascals when the volume is 1.4 cubic meters, find the pressure when the volume increases to 2.5 cubic meters. So we are given a couple of variables here. We know that V is volume and P is pressure. Okay, and then we know that P is inversely proportional to V. I don't know why I put a W, I meant V. So our equation is going to be P equals K over V. First thing we need to do is find K. So we know that the cylinder steam engine has a pressure of 960 kilopascals, 960 equals when the volume is 1.4 cubic meters, K over 1.4. So we're going to multiply 1.4. And then we want 960 times 1.4, which is going to be 1344 equals K. So therefore, our equation has become P is equal to 1344 over V. And we want to know, find the pressure when the volume increases to 2.5 cubic meters. So pressure is equal to 1344 divided by 2.5 cubic meters, which is going to be equal to approximately 537. I don't know why I would draw 6. 537.6, and the units of pressure were kilopascals. Kilopascals. Okay, so that is direct and inverse variation. Not super hard, but the application problems can be tricky. So remember, you just need to solve for K and that you are given enough information in the problem. So just take it slow, do a bunch of practice problems. You'll get more comfortable with this idea. You'll do better. It's going to be great. So that's 7.7, and that is officially the end of chapter 7. So remember, check in with yourself and see how well you understood the chapter. And that is all I have for you today.